So we're going to look at here is Young's double slit experiment and an example of how to calculate the wavelength of the light. So in the lab we had a laser, and that laser was travelling in this direction, and these waves here are the wavefronts that are propagating towards the screen. So here's your screen here, and that's a diffraction grating, and we had a distance in that diffraction grating of, I don't know what it was, but let's use an example here of say 1300 nanometers, which is 1300 by 10 to the minus 9 meters. The waves pass through, and Hugo's principle then says that they'll propagate behind that screen in this sort of a direction, and then they'll hit the screen and form a pattern that looks something like this here. And we would have seen this on the wall. Now the distance between here, between the barrier and the screen, I'm going to say is 3 meters as an example. And the distance from the central maximum, and remember the central maximum is this central antinodal line. So the distance from the central antinode to the first antinode up here, let's say is 1 centimeter, so 0.01 meters. So we have, so we have D, which was 1300 nanometers. We have the distance between the screen and the barrier is 3 meters, and the distance between the first antinodal central maximum and the first antinodal point is 0.1 meters. Now when we did the sound example last term, like the example that we did in the exam, you would have noticed we use the the nodal point. And the reason why we use nodal points when we're talking about sound is because the nodal point is where you have less sound, so it's easier to find that point. Now, in this case here, the bright spots are the antinodal points, and it's easier to see the bright spot. So we're going to use the antinodals. Last time we had the formula sine of theta was equal to n minus a half wavelength over d, but that is for the nodal points. And like we just said, we're going to actually use the antinodal point, so we're going to get rid of that minus a half, because now we're talking about the whole nodal point. So how are we going to solve this? Well, if you look at the distance between this point here, let's call that x over here, is 0.1 meters, 0.01 meters or 1 centimeter, and the distance along here is 3 meters. So we can actually go and draw a triangle here, there to there. This is out a little bit so that you can see it, and we're going to call that angle there theta. So in this case here, that theta is, let me get a different colour, that theta is the angle in between here. We want to try and figure out what it is. Well, we've got this side here, which is our adjacent side. We've got this one over here, which is the opposite side. And if we go back and look at a bit of trig, we know that the tan of theta is equal to the opposite over adjacent. And in this case here, the opposite side is 0.01 meters divided by the adjacent side, which is 3 meters. And if I go and work that out, and I say that the theta equals tan to the minus 1 of 0.01 divided by 3, which is 0.003, then theta is actually going to work out to be 1.91 degrees. Now that's important, that number there. That's the angle up in here. And it's also this angle here. So we're now going to go and say, well, the sine of theta, in this case now, theta is actually 1.91 degrees, is equal to n wavelength over d. So sine 1.91 degrees equals, and we're talking now about the first nodal point. This point here is the first nodal point, antinodal point. So it's actually 1 multiplied by the wavelength over, and the d is the distance between the diffraction grating slits, which was 1300 by 10 to the minus 9 meters. We can rearrange that formula. We say, well, sine of theta, or sine of 1.91 degrees, multiplied by 1300 by 10 to the minus 9 equals 1 times lambda, which is lambda. And if I go and calculate all of that out and multiply it out, then the wavelength of light in this case here is actually 3 by 10 to the minus 9 meters, which is 3 nanometers. Now once I've got the wavelength, in this case here, which is 3 nanometers, I can use the formula that we did last term, which was the speed of a wave, and that formula was V equals F lambda. And if I use this formula now, I can go and rearrange it for F, where the frequency is actually the velocity over the wavelength. Now the velocity, we know what the velocity is because it's light, and light is a constant velocity. And so we can actually say that F is c over wavelength, where c is the speed of light. And that's going to be then, the frequency is 3 by 10 to the 8 meters per second over the wavelength that we just calculated, which is 3 by 10 to the minus 9 meters. And the frequency, if you go and calculate that out, turns out to be 1 by 10 to the 17 hertz. So now we have the frequency as well. We have calculated the wavelength of the light and then the frequency of the light just by using the distance between the central maximum, this point here, and the first antinodal point, that point there. That is all.